This is the Sourcery CodeBench IDE, where an embedded software developer would edit his source code and compile it into the final executable program. On the right side, we can see everything defined in this module. By double-clicking on main, I can move the viewpoint to main. Now I'll finish writing my code, save this file, and build my application. Once the program is built, I can debug it with a number of different execution vehicles, including Vista Virtual Prototype, the Qimu target, Veloce RTL emulation using CodeLink, Veloce RTL emulation using a virtual JTAG probe, FPGA prototype using a JTAG probe, or the final board using a JTAG probe. In this case, since I haven't got any hardware, I'll choose to debug on the Vista Virtual Prototype. Now CodeBench starts the virtual prototype simulation and the debugger and moves into the debug perspective. As I step through the code, changes to variables are highlighted in the variables view. Now I'll step over the initialization code up to the basic packet test. Now I'll step over the basic write function. 10 bytes were sent, and I'll step over the read function. 10 bytes were received. The status OK indicates that they were correctly received, so the basic packet test worked fine. So now I'll step a little bit further, clear my counters, and start a long packet test. In this case, I sent 65 bytes, but it reports 66 bytes because the write function appends a null terminator to the packet. Now I'll step over the read function to read the bytes, and something went wrong. I got a status bad and 0 received bytes, so something went wrong with my test. A casual inspection of the code reveals the source of the problem as a cut and paste error. I already finished the basic packet test and I'm trying to do the long packet test, and I called the long write function but the basic read function. So now I'll quit the debugger and fix my code bug, save the file, and rebuild it. By clicking on the debug button, CodeBench will rebuild the application first, then relaunch the virtual prototype simulation, relaunch the debugger, and take us to the beginning of main just like before. Now I can step over the initialization code and step over the basic packet test. 10 bytes sent, 10 bytes received. Clear my counters. Step over the long packet test. 66 bytes were sent. 66 bytes were received. The status is OK. So the long packet test works too now. So we'll move on. The next thing is we go into a loop sending a lot of random sized packets with random data. So I'll set a breakpoint at the end of the loop and I'll run through the whole packet test loop. Now I've hit the breakpoint, and by checking the status is still OK, I know that my random packet test passed. So now I can carry on with debugging the rest of the functionality in my system. Advancing the software development schedule using simulation platforms such as Qimu or Vista provides obvious benefits to the overall project schedule. Using Vista Virtual Prototype also enables system analysis capabilities to ensure the design will meet performance and power budget requirements. As the software runs on the virtual prototype, execution is logged alongside estimated power consumption to show power usage over the run correlated to where the code was executing at any given moment. The Sourcery Analyzer perspective allows me to look at a number of performance metrics by picking from the Sourcery Analyzer agents list on the right-hand side. Here I'm looking at the function call graph, which shows me where my code is executing, and I'm looking at the VP power analysis graph, which shows me how much power is being consumed. One thing I notice in the power analysis graph is a repeating pattern of higher and lower power readings, and it seems roughly correlated to the function call activity shown below. So let me zoom in, and yeah, there seems to still be a pattern. Let's just look at 4 periods. And we can definitely see a correlation between function call activity in the bottom graph with periods of higher or lower power consumption in the upper graph. By adding function call traces below the power analysis graph, I can see what functions are active during the periods of high power usage. Here we see that when we're frequently calling the rand function, the power is higher than at other times. Since frequent calls to the random function seems to be responsible for the high power consumption, I'll rewrite my application to reuse a pre-computed buffer of random data instead of regenerating the random data on every loop iteration. After optimizing the software and rerunning the performance analysis, the power graph looks much less variable than it had in the first run. Zooming in, I do still see some power spikes associated with calls to the random function, but the power spikes are much narrower now because we call the random function much less frequently. The power analysis results from the optimized code certainly look a lot better, and by using the measurement tool, we can quantify just how much better. In session 1, the measurement tool shows an average power consumption across the run of about 117.5 milliwatts. By comparison, in session 2, the average power consumption over the run was 101.5 milliwatts. That equates to about a 5.6% improvement in power consumption.